So we were talking during class yesterday that as far as L'Hopital's rule is concerned, I really only ever want you to use the strong form, okay, which says that if we take the limit as x goes to a of f of x over g of x, and that, see, this board is still off, and that's equal to some indeterminate form like 0 over 0, which is pretty equivalent to infinity over infinity. We'll talk about some other forms today, that we can say that this is then equal to the limit, and this is the big difference between the weaker form and the stronger form, is that it's equal to the limit of f prime of x over g prime of x. And we talked about how this let you apply L'Hopital's rule over and over and over and over and over again, as many times as you needed to. So we're going to forget about the weaker form, the baby form. You don't need that. But you do need to know this. And please remember to write in the limit part. That is very important, because we're not saying that f of x over g of x is equal to f prime of x over g of x. We're saying that the limit in both of those situations are equivalent. Okay, and that's a very big difference. Okay. All right, so there are other indeterminate forms. Okay, we have things like infinity times 0, infinity minus infinity, 0 to the 0, 1 to the infinity. These are not 0 over 0 or infinity over infinity, which is the indeterminate form that we need in order to be able to use L'Hopital's rule. So remember the things that we do when we come to a limit. What's the first thing you do? Plug in, maybe you get lucky. What's the next thing you do? You might have to do some algebra. It is infinity minus infinity. Algebra. And that's effectively what we're going to do to turn these indeterminate forms into 0 over 0 or infinity over infinity. It's not going to be as simple as canceling things out or doing some factoring, but basically what we're going to do is we're going to manipulate stuff. Okay? So for instance, in these situations down here, where we've got some kind of constant, some kind of real number raised to 0 or infinity, what we're going to do is we're going to rewrite things and solve the limit as x goes to a of the natural log of f of x. And if that's equal to some limit L, then as we'll see, that means that my original limit is going to be equal to e to the L. Okay. No. We'll do some examples, okay? Because every limit I give you isn't going to be a fraction, okay? I could give you a limit, and that's one of the first, it's not the first example, it's the second or third example that we'll do. I could give you something that's a polynomial to the x minus 1, so that what you're going to end up with is 0 to the 0 when you substitute in x equals 0 or x equals 1 or something. Okay, so it doesn't have to be two things divided by each other. I just need to make it look like that. And I may very well be able to do that by doing this manipulation. Okay. If we've got 0 times infinity or negative infinity, then we're going to do some substitution. And we're going to sub in and let x be equal to 1 over h. And then change the limit. So that instead of having the limit as x goes to a, now I'm going to take the limit as h goes to 1 over a. And that may change some things for us. And when I end up with infinity minus infinity, I'm going to try to find a common denominator. So that maybe I can end up with f of x over g of x, and then be able to use L'Hopital's rule. Okay. So my goal in manipulating here, and manipulation might be a better word than algebra, is to turn it into a fraction that I make equal to 0 over 0 or infinity over infinity when I try to evaluate the limit. Okay. Just like when we were evaluating integrals, the goal was to come up with an integral that I could solve by inspection and use my tools to manipulate the form into something that I could recognize. All right. So let's try a couple more problems and see how this works. It takes a little practice. I will make sure tomorrow that I have practice sheets for you to take home and do before the quiz. So let's do page 454, number 15. Bless you, bless you. Okay. So this one is the limit as x goes to infinity, I think, of the natural log of x plus 1 over the log base 2 of x. So I am presented with a limit. What's the first thing I do? Substitute in. So if I substitute those in, what am I going to get? Well, obviously I'm not going to care that it's infinity plus 1. But what's the natural log of infinity? What does the graph of natural log look like? What? Yeah, it just keeps getting bigger and bigger and bigger and bigger and bigger and bigger and bigger, right? So what's this going to give me? Infinity over infinity. Okay, which is an indeterminate form that I can just apply L'Hopital's rule to. But let's do a little review first. And let's turn that log base 2 of x into a natural log, because who the heck wants to deal with log base 2 of x? All right, anybody remember that formula? You should know that formula. That is a very useful thing that you should know. It may be the sticky note sticking out of your textbook. Okay, because I often make classes sticky noted. Okay, and I see many of you have it. It's in Maggie's book. It looks like it's the right place in Sarah's book. Okay. So that means that my log base 2 of x is going to be what? Yep. Okay. So my limit is really going to be the limit as x goes to infinity of the natural log of x plus 1 over the natural log of x divided by the natural log of 2. And that's kind of all sitting there in the denominator together. And since I know that this is still going to be infinity over infinity, even if there's a natural log of 2 hanging around there, okay, I can apply L'Hopital's rule, which means I take the limit again, but now I'm going to take the derivative of the numerator and the denominator separately. So what's the derivative of the natural log of x plus 1 going to be? 1 over x plus 1. And then remember, I have 1 over natural log of 2 hanging out here. And what's the derivative of natural log x going to be? 1 over x. So I could substitute back in for my limit again. And what am I going to get? No, actually, it's not. Because what's 1 over infinity? 0. So actually, it's 0 over 0. Okay, which means, once again, I have an indeterminate form. And once again, I can apply L'Hopital's rule. So I've got my limit as x goes to infinity. And in fact, are they compound fractions? Is that what those are? They're not complex fractions, right? Because that would have like an I in it or something. Is it a complex? Like I said, I'm not really a math teacher. But like that bothers me. But I can rewrite this, right, as x natural log 2 over x plus 1. Never be afraid of a little algebra. Okay? I still get infinity over infinity. I still get an indeterminate form. Okay? So I can still apply L'Hopital's rule. But now what do I get? When I take the derivative, I'm going to have the limit as x goes to infinity. What's the derivative of the top? Priya? Of the top. What is it? No. ln of 2 is a what, Priya? It's just a number. So what's the derivative of the numerator going to be? ln 2. Okay. And what's the derivative of the denominator going to be, Rebecca? 1. Okay. So my answer is going to be natural log 2. Okay. All right. Bless you. Let's try something harder. So let's try number 23. Okay, so what do we have for 23? Okay, so I'm presented with a limit. What's the first thing I do? Substitute in. Okay, so if I substitute in here, what am I going to get? What is it? 0 to the 0, right? 1 minus 2 plus 1 gives me 0. 1 minus 1 gives me 0. That is not equal to 1. Okay? Like anything to the 0 is equal to 1, not so much. Okay? So that's an indeterminate form. Actually, I believe the answer is 1, but yeah, but you can't calculate it that way. Okay? So that's an indeterminate form. But it's not infinity over infinity anymore. Do we need to do this? Did everybody get this? We can do this. Okay. All right. So we need to put it into the indeterminate form. And we said that when we had something like this that involved powers, what we were going to do was take the natural log. So this whole thing here, exponent included, is my f of x. It's the thing I'm taking the limit of. So this is going to be then the limit as x goes to 1, but I'm going to take the natural log of f of x for a really good reason. So this is going to be the limit as x goes to 1 of the natural log of x squared minus 2x plus 1 to the x minus 1. And then what really cool thing can I do because it's a natural log? I can pull down the exponent and put it in front. Okay, so this is going to give me the limit as x goes to 1 of x minus 1 times the natural log of x squared minus 2x plus 1. Now, as Zoe was fretting about earlier, in order to apply L'Hopital's rule, I need a numerator and a denominator. What can I do to this to give me a numerator and a denominator? Zoe, what do you want to do? I most certainly can. Right? Because the denominator of a denominator is a numerator. And go ahead, Sarah. Yep, that's what I was going to say. You are presented with a limit. And the first thing you do is sub in. So, what do we get? No, actually you don't. What's the natural log of 0? Because remember, the argument of my natural log is still 0, right? It's actually negative infinity if you think about the curve. And what's 1 over 0 in the denominator? That's positive infinity. Okay. So I've got infinity over infinity, which means I can use what? L'Hopital's rule. Okay. So that tells me that my limit as x goes to 1, I take the derivative of the numerator and I take the derivative of the denominator separately. So what do I get when I take the derivative of the numerator? Okay, so it's going to be over whatever the original thing is, and then I take the derivative of what's inside. How about for the denominator? Yep. No, it wouldn't. Okay. Now, that should just scream algebra at you. Because again, I've come to a limit. I substitute in, and I'm getting all kinds of weird stuff, right? I'm going to get zeros everywhere. Many, many zeros. But what should immediately pop out at you is that I could take a 2 out of there, right? And I've got negative 1 over x minus 1 times x minus 1 there. And then what do you know about that polynomial? It is factorable. And what is it factorable into? Right, which means that this cancels with that. Because they're both in the denominator of their complex fraction. Which leaves me with the limit as x goes to 1 of negative 2 times x minus 1. And again, I substitute in. And what do I get when I substitute in? But what you have to remember is what you just figured out was that the limit as x goes to 1 of the natural log of f of x is equal to 0. Not the limit as x goes to 1 of f of x. Okay. So, if we want to find the limit as x goes to 1 of f of x, where f of x was that polynomial to the x minus 1, then that's equal to the limit as x goes to 1 of e to the natural log of f of x, right? Because e and natural log are what? What do we call those? Inverse operators, and they cancel each other out. Okay. And so I think you can say that this is really equal to the limit as x goes. I do not like this board today. No, as x goes to the 1 of the natural log of f of x. And I know what this is. What's that going to go to? That's 0. So this is really going to be e to the 0, which is equal to 1. I think I vaguely remember it being a property of limits. And it's because the only you're basically, remember, e is a constant. So basically you're taking it a constant and raising it to the function. So what I really care about in the limit is what happens to the thing that has the x's in it. So I could honestly, and what I usually do is skip right from this step to this step. But I kind of vaguely think that that kind of makes sense. Okay. All right, we're going to stop here because the bell's going to ring. The test is tomorrow. We will do our last examples on Friday.